Okay, so hi to everybody who's I hope a lot of people are going to watch this at home because there's a lot of people missing. Look at how many people are missing. So I better see like 7 or 8 views on YouTube. Okay. Yeah, I've been posting these things on YouTube. There's like 1. And I think that's me. Like, I've watched it. Naughty. Okay. So anyway, ocean water, structure, properties. It's okay because I'll use it. I'll use it for the rest of my life when I teach oceanography, and people can, if they miss class, they can watch this. Okay, now I got to find my place here. Oh, sediment. Oh, here we go. Ocean water and structure. Lecture assignment number 12. Okay, so first of all, we need to talk about water, and I hope it's not news to you that actual water molecules are H2O, right? So I hope you all know that. Oh, hi, welcome. Glad you made it. That sounded like an interesting day you had. Yeah. So anyway, let me mark you here, Bree. Okay. Okay, so it's H2O, of course, and you know that water has this very unique structure. Has anyone ever seen that kind of weird structure before, where it's got, of course, the 2 hydrogen atoms connected to the red oxygen atom, okay? And then it has that kind of weird structure where it has this angle between the, right? Has anyone ever noticed that before? You never notice it has that angle like that? That's the structure of the water molecules. Okay. Has anyone ever looked at that and be like, why does it do that? Like, why isn't it just, I wonder if I have any chocolate. Oh, wait, I do have chocolate. Has anyone ever wondered why it's not just like, here's the oxygen, okay? There's the oxygen atom. And then, why isn't it just like this? And then, that seems more, I don't know, seems to make more sense to me. Because actually, by the way, if you look at carbon dioxide, you know carbon dioxide, right? Okay, carbon dioxide is like this. It is like that. There's the oxygen. There's the oxygen, right? So, why isn't water like that? Did you ever wonder about that? Isn't that kind of weird? The polarity. The polarity, but it is polar. It happens to be polar, but actually, the thing that's causing it to be polar and the thing that causes it to have that special structure is the same. So we're going to talk about the root cause of both those phenomena. Okay? But yeah, you're right, it is polar. Okay, so water molecules are held together by covalent bonds. Covalent bonds. So that means that the oxygen is bonded to the hydrogens, right? The oxygen's bonded to the hydrogens. And what the heck is a covalent bond? So hopefully you've learned this maybe in high school or middle school, but to repeat it again, covalent bond is a bond where the atoms are sharing the electrons. It's where they're sharing electrons. That's different than the other kind of bond, which is called an ionic bond, because in ionic bonds, the atoms actually totally give up an electron to, so there's kind of a giver and a receiver. That's called an ionic bond. These are different. These are called covalent bonds, and the co means sharing. So the covalent means they're sharing what are called the valence electrons, which are the outermost electrons. So I want to go in a little bit about covalent bonds and also something called the octet rule. Well, kind of a strange thing about nature, and of course this isn't a quantum physics class, so I can't go into explaining why this is, but let's just take it for granted that atoms like to have 8 electrons in their outermost shells. Okay? Has anyone ever heard of this before in a chemistry class before? Amanda, you've heard it a little bit. Julia's heard it a little bit. Okay. And Colton's heard it a little bit. So atoms like to have 8 electrons in their outermost shell. You might remember that electrons are kind of split up into different shells that orbit around we kind of say orbit around the nucleus. Okay? So hopefully you've heard this before in high school chemistry or something like that. But I want to show you these little black dots represent the electrons, right? And this is actually showing carbon dioxide, CO2, okay? So here's the carbon, and carbon has 4 electrons in its structure, but it's going to share another 4 electrons with the oxygen, so it has a total of 8. So if you look at how they're sharing the electrons, this is oxygen, this is carbon. Okay, let's look at this oxygen. 1, 2, 3, 4, 5, 6, 7, 8, right? Happy, he's happy because he's got 8. That's what atoms like. And this is called the octet rule. Okay, so the next question is, what is an octet? An octet, what's meant by that is that it has 8 electrons in its outermost shell, and it's happy. That's what atoms are always trying to achieve. They're always trying to get that full 8 electrons in its outermost shell. Okay, the next guy here, the carbon, has 1, 2, 3, 4, 5, 6, 7, 8. He's happy too. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. It's happy too. Okay? So you see how that works. Okay, now I'm going to go over here. I'm going to show you with, let's do H2O now. Okay, let's do H2O. Does anybody happen to know off the top of their head which element oxygen is? It's number
16.
Oh, you're really close. That's the atomic mass. So if you divide that by 2, because it usually has 8 protons and 8 neutrons, that gives the atomic mass. So it's actually element number 8. Yeah, but you're on the right track. Okay, so oxygen is element number 8. So here's my oxygen for H2O, right? So how many electrons does oxygen have? It has the same number as protons, okay? So it's going to have 1, 2, 3. Is it number 8? Wait a second here. That can't be right. If it's number 8, it would have. Oh, I'm sorry. Okay. Not thinking the right thing. So it's going to have, the first shell is going to have 2. And the next shell is going to have 6. Sorry, I don't really do a lecture on like beginning chemistry in this class, so I hope the first shell has 2, this next shell has 6. Okay, so the outermost shell is going to have 6. Okay, kind of like that. So there's your oxygen. Okay, so does that make sense? All right, now the next one is going to be hydrogen. Hydrogen is element number what? Number 1, right? It's element number 1. So it has 1 electron. The other hydrogen over here has 1 electron, okay? So what's going to happen is that they're going to have, this hydrogen's going to go with that, that's going to go with that, they're going to share, okay? That makes sense? And it has 8, right? So it's going to have 8 in all their shells in the oxygen, and then the hydrogen is going to have 2 in its shell. And I know this is kind of weird, and again, it has to do with quantum physics, but it's okay for hydrogen and helium are happy with just 2, because they're the first energy level. So the first energy level is 2, the next subsequent level is 7. So anyway, they're all happy. So that's covalent bonding. Now, this is what I want to point out, okay? Do you notice how oxygen now just has these like extra pairs of electrons? So those extra pairs of electrons have what kind of charge on them? What charge do electrons have? Negative, right? So those negative electrons are going to be highly charged. They're negative charge. And what's going to happen is they're going to be repelled by the electrons on this side. And so what's going to happen is that the extra electrons that are not bonded to the hydrogens on the oxygen are going to stay on one side, and the hydrogen atoms, which are now have positive charges, because they're kind of more positively charged because now their electrons are being taken into the oxygen. Okay, they're going to kind of be on the other side. And so this is going to set up that unique structure that it has. And the reason is because the electrons repel each other. So does that make sense? So I ask another question here. Do electrons repel each other, or are they attracted to each other? Yeah, they're repelled. So these, what are called lone pair oxygens, are going to be repelled onto the other side of the oxygen, and then the hydrogens are going to be kind of clumped, more kind of clumped closer together. So you'll notice that when we broke everything down with carbon dioxide doesn't do that. It doesn't have the lone pair extra electrons in its shells that are not bonded. So that's why it actually doesn't have that. It has that straight structure instead of this structure. Right, so that's H2O. Okay, and again, it's because it has these extra lone pair unbonded electrons that are going to get pushed to one side, and then the hydrogens are going to get pushed to the other side. Okay, so I hope that makes a little bit of sense, but I think for the question where it says, why does H2O have this kind of angled structure versus a straight line structure? It has to do with the fact that it has these unbonded extra pairs of electrons in its outermost shell that are going to be repulsed and pushed to the other side. So you can put something like that for that answer. Okay? Carbon dioxide doesn't have that. You'll notice how the carbon, do you notice how the carbons, all of its electrons are involved in bonds with the oxygens? So there's no extra unbonded pairs. So I'm sorry if that kind of like makes no sense, but if you kind of requires some high school chemistry, so hopefully some of you might have taken that and remember it. Some of you maybe don't remember it very well, or maybe do you have to take chemistry in high school? Yeah. You have to take some, right? So hopefully this doesn't sound totally unfamiliar to everybody.
It doesn't, but I just don't remember.
Yeah, that's fine. So, but hopefully it makes a little bit of sense. I just hope that you can see the difference. I guess the difference kind of comes here, like between carbon dioxide and H2O, is that all of carbon's electrons are involved in bonding, whereas that's not true with H2O. It has kind of extra unbonded electrons that get pushed to one side of the molecule, and then the hydrogens get pushed to the other. Okay, and it has to do with that electrons repel each other within their orbits. That's my email. Sorry. I should shut off my email when I lecture. All right, so now we're on to, we did number 5. Hopefully you could put something to number 5. And let's talk about something Colton brought up. He mentioned about the polarity of water, right? Didn't you mention that?
No.
Oh, sorry. Who was that? Was that? Somebody said. Okay, it's okay. Oh, Liam mentioned. Sorry. I thought it was. I'm getting you too confused. So anyway, talk about polarity of water. Okay. There's my clicker. All right. So chemical bonds formed by sharing of electrons. Electrons shared to form octets. Atoms within covalent bonds are electrically neutral, nearly so. Okay. So we talked about all that stuff. So sharing of electrons in H2O allows each atom to fill its outermost shells. Okay, so that's kind of what I drew right there, right? So hopefully you see the similarities. I kind of drew a similar drawing. Yeah. So hopefully it all makes sense to you up to number 6. So we're on number 6. Okay, so by the way, there is a very constant 104 degree angle between the hydrogen atoms in a water molecule. Okay, so do I ask that specifically? What's the angle? I don't know if I do. Maybe I don't. But that's what it is, 104 degrees. So there's a 104 degrees between those two oxygen atoms. Oh, and look, and it gives the average distance between the oxygen and the hydrogen. 95.8 pm. What's a pm? It's a picometer. Picometer. It's 1 trillionth of a meter. Meter divided by a trillion. Picometer. Okay. Polar molecules. Okay, so I hope that you can see that if you have the electrons, kind of like the extra free electrons, kind of grouped up on one side, what's the charge on the electrons? Negative, right? And then you have the hydrogens, which have now kind of, they're sharing their electrons now with the oxygen. And so those electrons are not spending as much time over here in hydrogen town. They're kind of going between hydrogen town and oxygen town. So this is going to be more of a positively charged area. Okay? So if you take a look at this side of the oxygen is going to be more negatively charged. This side is going to be more positively charged. So that's what we mean when we say that water is a polar molecule. Just like we on Earth, we have a north pole and a south pole, right? We have poles. And we have, and it's kind of it's a magnetic pole, right? We have a plus and a minus in a way. So it's the same thing here. A water molecule is it's going to have a more negative side and it's going to have a more positive side. So it's going to have a more negative side and a more positively charged side. So here's something for you to consider. If this has a negative side, and this is more negative and this is more positive, what do you think is going to happen? Do you think that the negatives are going to want to get with the positives?
Maybe.
Yeah, big time. Because opposites attract. Yeah, not just maybe, but they're gonna love each other. They're just gonna be all over each other. So the negatives, the negative sides of these atoms are gonna want to, these molecules are gonna want to attach to the positive sides. Okay, so does that make sense? Because you know how magnets work, right? Have you ever tried to push the negative or like the positives, the two positives of a magnet together? They just won't go together, right? Or if you flip the magnet, they stick right together, right? Because the opposites are attracted to each other, whereas the ones of the same polarity repel each other, right? So anyway, you're going to have a negative side and a positive side, and these oxygen, what you're going to find is these these water molecules are going to love to get all hooked up and connected together. And we call those things, those connections, hydrogen bonds. We call them hydrogen bonds. And you're going to see that this polarity of the water molecule and the hydrogen bonds create so many very unique phenomena with water. Does anybody know off the top of their head something special about water? There's something really special about water. Actually, you'll see a lot of really special things about water. But can anybody name anything kind of special that water does that's very unique? There's actually a lot of things it does that are very unique that we're going to learn about. But
It expands when it freezes.
yeah, that's one thing. It expands when it freezes. That's weird. That's not normal. Nothing else, not nothing else, but very, very few other things do that. What was that?
Evaporate?
Yeah, it evaporates, and actually it evaporates, but there's a huge energy change when it evaporates. And we're going to learn about that too. There's a lot of very unique properties of water, and they are all connected to this fact that it is so polar. Okay, water is so polar. And it just makes a lot of strange phenomena. And like they're phenomena that we're used to because water's everywhere and our bodies are even mostly water, right? But, so we're used to them, but they're actually very, very unique among molecules and different chemicals of the Earth. So water is it's a chemical, of course, that we're very used to, but it's a very unique chemical in the whole universe, actually. So we're actually spend a lot today talking about why water is unique. It is very unique. So you can see that the hydrogens are going to like to bond. The plus sides are going to like to bond with the negative sides. Okay? And see all those little dashed lines, those are all the hydrogen bonds. Okay? So where am I at now? So water is it's a polar molecule. And what does that mean? It means that it has a plus side and a minus side, right? And then it says, why is water such a potent molecule capable of dissolving rock? You're going to find, by the way, on the test and on this lecture assignment, when in doubt, just put it's a polar molecule. it's an answer to a lot of questions. Okay? It explains a lot of things about water. So why is it? It's a polar molecule. It's good at dissolving rock and dissolving all sorts of things because it's polar. Now, why do water molecules stick together? They stick together because it's a polar molecule. And there's hydrogen, it forms hydrogen bonds.
So we rank the same answer?
I think actually the rest of the answers to this are because it's a polar molecule. No, I'm just, but it is an answer to a lot of questions. Okay. It's actually good. Yeah, I'm reading this. It's kind of embarrassing. So a lot of these are just because it's a polar molecule. Okay, so let me talk about some of the weird things about water. So you have to remember that water molecules like to stick together and connect together and get all hooked up and linked up. And why do they like to do that? Because it's a polar molecule and it forms these hydrogen bonds. Okay. So you've probably seen water do this before. Okay, that's actually very unusual for liquids. Usually liquids don't bead up like that necessarily. Has anyone ever, and you kind of know this, like if you pour oil, like if I were to pour some oil on the, it's not going to bead up like that, right? It'll kind of turn into a big oily pile. Right? That's what oil would do. But water will like to bead up that way. Why? Because they like to connect and be all connected together, and they form up like perfect little spheres, right? So they don't want to be all spread out. They want to be all jumbled up close together. And you've probably seen creepy little things. There's a creepy spider walking on the water. I found that and I put that in there in the corner. But you've probably seen things like this before, right? Bugs walking on the water. They can do that because of surface tension. And why does water have surface tension? That's something unusual. It's not typical of, what's that?
Oh, because it's polar.
Yeah, because it's a polar molecule. That's why. So why can bugs do that? Because it's, like I said, it's not normal. It's not normal. Most liquids don't do this. Like if this was, don't think you could do that on molten lava or something. You would have surface, you would just sink right in. So you don't want to do that. But, I mean, among other reasons. But most things, you're not going to have surface tension. Here's kind of a neat picture. That's right before a swimmer's face comes and like breaks the surface tension of the water. I just thought that was a pretty neat picture. But you can literally see it almost looks like it's like latex or like a plastic, what do you call that, plasti wrap or something. He's like pushing his face in there, or he or she, I can't tell you. But yeah, but that's, again, it's resistance to breaking the surface tension. It's because of the hydrogen bonding. It is also the universal, we call water the universal solvent. We call it the universal solvent means that it can dissolve just about anything. And it can dissolve just about anything because it's just, you can imagine how ferocious it is. Because look, it's got a real strong negative side and a real strong positive side. So it allows it to go in and break bonds. And break the little molecular bonds of rocks or ionic solids or crystals or anything. Given enough time, water can destroy just about everything, and you know that too, right? If you leave a car, bicycle or whatever out in the elements exposed to the rain and the water, boy, it doesn't take very long for it to just break down completely, right? Water's very potent, very powerful molecule. And the same goes for rocks. Rocks seem like they're really tough, strong materials, but it doesn't take really that long for the rocks to get worn away and dissolved away by the water. And that happens all the time, right? The shoreline is getting eaten away and dissolved away by the water. So even solid rock is susceptible to erosion and weathering and breaking down by the water. Okay. So that polar structure of water allows it, what happens is it will, see, like here's the plus minus ions of like a rock. Okay, it's composed of all these ions. What will happen is you can see that negative ion gets totally surrounded by the positive hydrogens of the water molecule, and that's how it dissolves it away. Okay. Now here's another thing you've probably seen before. If you ever made salad dressing, does anybody like to make vinaigrette? Oh, okay. There's some vinaigrette fans in the front. That's good. Okay, well, if you ever tried to make vinaigrette or salad dressing with oil and vinegar, you know that it doesn't mix, right? Or oil and water don't mix, okay? So again, that's because oil is a non-polar liquid. Oil is a non-polar liquid. And water is a polar liquid. And because oil is a non-polar liquid, it's sort of immune to water's power. So you know, a lot of times when you want to defend something from attacks by water, you'll cover it with some kind of hydrophobic, basically sort of like an oily layer or something. You know, think of latex paint. You know, you put like latex paint is kind of is non-polar material, right? And it repels the water. Or a lot of times we put coating. We also put all sorts of coatings on things to protect them from water damage, and a lot of those are non-polar materials. So oil is a non-polar molecule, cannot be pulled apart by the polarized water molecules. It's what an oil, kind of a typical oil molecule looks like. Okay. So now we're up to number 11. So I talked about a lot of kind of weird things about water that arise from its polarity. And you're going to learn even more things. We're not done yet with the strange aspects of water. Okay. Another thing we want to talk about now, move to now, are the states of matter of water. Now, of course, the oceans are liquid water, but we also have, you know, ice as well, the solid phase, and we have water vapor, which is also it's the gas phase, right? And I want to make something clear. Water vapor is actually invisible. You can't see water vapor. A lot of times people think that clouds or fog, they think that's water vapor, but actually those are minuscule droplets of liquid water, or in the case of clouds, in the case of high clouds, they're actually usually ice crystals. Okay. So I kind of show this to represent the water vapor, but I have to show something because you can't see real water vapor. So is there water vapor in this room right now? Yes, there is. There's water vapor, and that creates the humidity. Have you ever heard that term before, humidity? Okay, the humidity is literally referring to how much water vapor is in your room or in the atmosphere or whatever. Okay, it's how much dissolved water is in the air at the time. Dissolved water vapor. Okay, so when water changes its phase, that means it goes from solid, liquid, gas, solid, liquid, blah, 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 blah. There's always going to be an energy transfer. There's always going to be an energy transfer. Okay, and you'll see that number 11, I say, look at the labels of the arrows. I'm showing, you know, going from ice to water to vapor to back and forth. And I say, name the two processes that correspond to each phase change. Okay, so a lot of these, hopefully you know this already. So let's do the first one. Ice goes to water. What do you call that? Melting and then freezing, right? So y'all know that. Now, water goes to water vapor. What are the two processes? So water goes to water vapor and water vapor goes to liquid water.
Precipitation.
Yeah, evaporation and precipitation. Right? We're going to use a different word. We're going to use condensation. Precipitation is actually a little different than condensation. Wow, I thought this was going to take until the next class, and look at that. So it's already at the bottom, basically, huh? So it already dropped out of the water column. And this one too. Can you all see how it's clumping near the bottom? And, oh, look, you actually see the little pieces of sediment falling out, slowly falling like snow to the bottom. It's kind of cool. So you're up close instead. Okay, now here's kind of a weird one that probably I would be very surprised if anyone knew the name of these processes. So do you see how it's actually possible to skip the liquid phase and go directly from solid to gas and gas to solid? So when you go, does anybody happen to know what those things are called? Do I have, oh yeah, I do have it here. So going from an ice to a water vapor, we call that sublimation. And going directly from water vapor to ice is called deposition. Okay? So for each of those arrows, you need to have the two processes, the two, because there's a back and forth. So did everybody get that for number 11? Everyone got the answers? All right, now, I said earlier, and this is very important, I want to make this just really, I just hope everybody's really listening right now, because this is very important, and it's going to be important almost like every lecture from here on out as we go forward. It comes up again and again and again. Because of the polar molecules, the polarity of these water molecules and the hydrogen bonding, every time that water changes phase, that means it goes from water to gas, gas to the solid, there's a phase change, right? Change in the state of matter. Every time that there's a phase change, there's going to be an exchange of heat energy. Either there's going to be absorption of heat or release of heat. Okay? We call that heat exchange when water changes phase latent heat. It's called latent heat. So you notice number 12, I'm asking, you kind of have to go back to the diagram on the previous page. And you have to answer, how is energy exchanged between each of those, in each of those processes? So let me show you. So when water goes to water vapor, does that break hydrogen bonds or does that form hydrogen bonds? It breaks hydrogen bonds. Okay. So when you break a hydrogen bond, do you think that's, if you had to guess, do you think that's going to release energy or do you think that's going to take energy to break the bond? It's going to take energy to break the bond. Does that make sense? So think about this. We go from water, which has a lot of hydrogen bonds, to water vapor, which has virtually no hydrogen bonds. And we're going to have to break hydrogen bonds, and it takes energy to break the bond. So if it takes energy to break the bond, that means that where is it going to get that energy? It's going to take it from heat from the outside. So what's going to happen is that all these molecules are going to absorb heat. They're going to absorb outside heat, and they're going to use that heat from the outside to break the bonds, and then go to the water vapor phase. Okay, has anyone ever? Okay. When you boil water, I should say, has anyone ever boiled water before? I hope you all have boiled water before. So when you boil water, you might know that, have you ever thought about this? What's the temperature of the water when it's boiling? What's the temperature of the water when it's boiling? 100 Celsius, right? Okay, what's the boiling point of water? It's not a trick question. It's 100 Celsius. So have you ever thought about this? The water's at 100 degrees Celsius. The boiling point of the water is 100 degrees Celsius. So why doesn't it all just poof, turn into steam? Why does it take time to boil it off and boil it off and boil it? It actually takes a long time and a lot of energy. I mean, how long do you think it would take if you put that on your burner to burn off a whole pot of water? 30 minutes or 40 minutes or hour or something? It would take a long time. Or even at full temperature, it would take a long time, right? Full heat. Where is all that energy going that you're pouring into the pot of water? But you're not changing. Do you ever notice you don't change the temperature? So if I boil that for an hour, does the temperature change? Or is it still 100 degrees, right? So you could have that pot of boiling water. You're pouring energy into it, and yet it stays at the same temperature. Do you see the paradox there? So where is all that energy going? Because energy can't be destroyed. It can't be created or destroyed, right? It's one of the fundamental truths of our universe. Where is all that energy going to? Because we're not changing the temperature.
We're trying to break the bond.
You're breaking the bonds. Okay, it's all going into breaking the bonds. So to break the bonds, to go from water to water vapor, you have to break bonds that takes energy, that absorbs energy from the environment, from the outside. So it's bringing energy in, sucking it up, and it's breaking those bonds. It's using it to break the bonds. Okay? Now, think about this. What happens if you go from a solid to a liquid? Are you breaking bonds? Or what has more bonds, the ice or the water? Which has more hydrogen bonds?
The ice.
The ice has more hydrogen bonds. That's correct. So are you breaking bonds when you go from ice to water? You're breaking bonds, which means that you have to suck, right, all of that energy out of the environment to melt your ice. So when ice is melting, it's actually making, not only is the ice cold, but it's also taking and sucking energy out of the environment to melt the ice, because it wants to break the bonds. Okay? So it's taking energy away from the environment around it. So not only is it just cold, but it's literally making it colder, making your environment colder. And that's actually, by the way, you can actually kind of set up like an ersatz air conditioner for a house by getting like if you could get like a huge tank of ice, and you could put like a fan. So if you had a fan kind of blowing air like this in and out, let's say you had 2 fans set up like that to keep air circulating. And then you just had like a huge tank, doesn't have to be huge, but you had ice, right? So that's all filled with ice. To melt that ice, it's going to be sucking energy out of the atmosphere. So you can actually build kind of an ersatz air conditioner out of that. Same thing happens too, but has anyone ever heard of a swamp cooler? They're not a big deal here because it's too humid to work here, but like in Arizona and where there's a lot of dry heat, there's a way of air conditioning that uses condensation of water. It's okay if you haven't heard of it. All right, so these changes in heat are called latent heat, right? So to go from ice to water, you have to add energy. That means it takes energy in. That means it's going to cool everything down. You know, I kind of don't like the color of these arrows because I feel like they're counterintuitive. I kind of feel like these should be blue because you have to add energy to break the bonds, but that makes everything around you cooler. So it's taking energy from the atmosphere or your environment to break the bonds. So it takes energy to break the bonds, to break the hydrogen bonds, and it's going to make everything cooler because where is it getting that energy? It's getting it from the environment, from the outside. Okay, so it takes energy. Now, on the other hand, to form hydrogen bonds, when you form hydrogen bonds, it actually releases energy. So these processes will actually make it hotter, make the environment hotter. Okay. So going from water vapor to water, so that's called condensation. It's going to make things warmer. It's going to release the latent heat. Going from water to ice, that's called freezing. That's actually going to, believe it or not, this is kind of a counterintuitive thing, but when you go from water to ice, you have to form hydrogen bonds, and that will release energy. It's actually going to release energy. So I know this sounds very counterintuitive, but when water is freezing, it's actually heating up and releasing energy. So actually, one thing you might have seen before, I'm going to show this to you later. I guess I'll get to it eventually, but during a freeze, some places, they'll actually saturate the ground with water, add a lot of water, because the water freezing will help to slow down the temperature drop. Because as it freezes, the water freezes, it will release energy. So I'll show you some real agricultural examples of that. They actually do that in some places to combat a freeze. Okay, so one thing I wanted to talk about here too, a little bit, is the difference between heat and temperature. Okay. Heat is the amount of energy stored inside something. It's the amount of energy that it contains. Temperature is just a measure of how hot or cold something is. So I wanted to show you this. This guy has a red hot poker there. Now that maybe has a very high temperature, but it actually doesn't have very much heat. What has more heat is this boiling water. Boiling water actually has a lot of heat. It doesn't have as much temperature. It's not as hot, but it has more heat. It actually contains more energy. Okay, so that's the difference between heat and temperature. Sorry. Probably people telling me why they're not here. Okay, now number 14. It's kind of obvious, but I want you to think about the difference and relationship. You know, we tend to think of temperature, like hot and heat, as the same thing, right? And I'm trying to make a distinction. There's actually a difference between those things, okay? Now, we can actually make a graph of H2O as we increase the amount of heat. So I want you to imagine we're going to start off with ice. And it's going to be ice, let's say at 0 degrees, okay? Or maybe it should be below 0 degrees. Let's say it's negative 30 degrees Celsius. So it's below the freezing point, okay? Now, I know I didn't put any numbers on here, and you don't really need numbers per se, but we could maybe add some here. So let's just say this is, negative 30 degrees Celsius, okay? So what's going to happen to the amount of heat as I raise, or let's do it the opposite. Let's say I start adding heat to my ice. I start pumping heat into it, heat energy. I put it on the burner. I get a, what do you call it? A frying pan of ice, and I just start putting it on the burner, and I start adding energy to it. So what's going to happen to temperature? It's not your question. Temperature is going to rise, right? Temperature will rise as the heat rises, right? So it'll rise. But then something happens. At 0 degrees Celsius, what happens as I keep adding? Remember I talked about this? I said you're gonna pour in all this energy, but the temperature's not going to change, right? So at 0 degrees Celsius, I'm going to start melting, right? And I melt, but my temperature does not go up until everything is melted down to the last little shard of ice. When that last little shard of ice melts, then my temperature starts going up again, okay? So now my liquid will start rising in temperature. And it'll go up, and up, until I get to what temperature? 100 Celsius, right? And then I start to boil, okay? So vaporization turns into vapor. And then it's going to flatline. I'm going to put more heat, but it's going to flatline until everything is evaporated. And then after that, then the gas, now of course the gas normally is going to float off, but let's say I have a frying pan that's like enclosed. I guess you could imagine like a pressure cooker, really. A pressure cooker would probably be a better example. Well, you know what? We can actually make that gas, water vapor, even hotter than 100 degrees Celsius. And actually, I don't know if you know this, but steam can burn you a lot worse than water can. I don't know if anyone's ever gotten a burn just from the steam, but because the steam can get hotter than 100 degrees Celsius, right? So steam can be pretty dangerous. Okay, so that's showing you Now you'll notice there's a certain slope here, right? Do you see that slope? That's actually giving you, do you all remember rise over run from algebra? Rise over run, right? Oh, is that nobody, you don't love rise over run? No? Okay. I'm sorry. So the rise, you hate it, okay. So the run is the change in the heat, right? Do you all see I put that, do you love that delta symbol? Remember that's the change in? So that's change in heat. And then over here is the change in temp, right? So the rise over the run. So that's the slope, right? That's the slope of that line, okay? So that change in heat over the change in temperature, and I know that that's actually run over rise, but that's okay. That change in the heat over the change in the temperature, that's a very unique number for every single different kind of material. Okay, it's not constant. It matters what kind of material you're talking about. That slope, the change in the heat with the change in temperature, is called the heat capacity. Bless you. The heat capacity or the specific heat. Okay? So that's the answer to number 15. It's the change in the heat with the change in the temperature. It's how much heat changes with temperature. Okay, again, notice how these lines, these slopes plateau at the heat, at the melting point and at the fusion point, the vaporization point. That's because all heat goes into breaking the hydrogen bonds, the intermolecular bonds. They're called the hydrogen bonds. Okay, so that's where all that heat is going. It's going into breaking bonds. All right, now, does anybody know this movie? Nobody knows this movie? Airplane. Thank you. Glad somebody knows. If you haven't watched Airplane, I highly suggest it. Zucker Brothers. It's the 1970s. It's kind of old. It's all right. But anyway, that's Robert Hayes. I don't know if you know this, but you have really good thermoregulation capabilities. As a human being, as a human, part of the human family, you have excellent thermoregulation capabilities. No other animal on Earth can regulate its temperature like you can. You're the best. Not only are we the smartest animals, but we also have, for some reason, I don't know why, we're the smartest, but then also what's the other thing that's outstanding about human beings? Great thermoregulation. No other animal in the kingdom can compete with us. We're the best. So anyway, you do a lot of this. Some people do it more than others. But actually what you're doing is you're taking advantage of the latent heat. Okay, so what happens is that your body secretes sweat, right? Liquid water, mostly liquid water and other gross stuff. And it secretes it onto your skin, and then it evaporates. And when it evaporates, it breaks the hydrogen bonds, and it's going to suck heat right off your body. And so, sometimes, boy, if you're really hot, sometimes people, you could almost see them steaming. They're like steaming hot. If they're like playing basketball or something, you could literally see them steaming. You get steaming hot. And all that is evaporation off your body to keep your body nice and cool. Most animals can't do that. They can't sweat like we can and remove heat so effectively as us. So that's why, we have good endurance. Most animals can't run a marathon. We can run marathons. Most animals can't run for just 5 hours without stopping. You can't gallop a horse for 5 hours without stopping. The horse would be blown in no time, right? So, has anyone ever read Black Beauty? Yeah, you have? Okay. There's a part in the Black. Do you know what I'm talking about?
That was like in middle school.
Oh, it's in middle school. Okay, never mind. I like that. You know what? Maybe I'm thinking of it because I just read it to my 7-year-old, so that's fine. So. to get that off his face. Okay, so those slopes, those are the change in heat with the change in temperature. That's called specific heat, aka heat capacity. Now, something about water is that I want to show you some things. Here are some heat capacities, or actually I guess these are specific heats. So it's how much energy you've got to put into a substance to change its temperature. How much energy do you have to put into a substance to change its temperature? Now here are some different materials just for comparison. Gold. Does it take much energy to change the temperature of gold? No, it doesn't, right? Gold's teeny weeny little specific heat, very small. Lead, silver, brass, copper, a lot of these metals, it seems like it doesn't really take much energy to change the temperature. They heat up pretty fast. And probably you've noticed that before. Do you ever put a pan on the burner? The metal pan, it heats up pretty fast, right? It doesn't really take that much time to get it hot. It takes a long time to get the water in it hot, right? But it doesn't take much time to get the... Okay, so there you go. Granite, okay, takes a little bit more. Paper, leather, oak wood. Oh, it takes a lot of energy to change the temperature of oak wood. I didn't know that. Okay. So now I'm going to put water on here. Okay. I'm going to put the specific heat, aka the heat capacity of water. How much energy does it take to change the temperature of water? I'm going to put it on here. Look at that. Way more, huh? This has to do, again, why? Because it's a polar molecule and it has these hydrogen bonds. And those hydrogen bonds suck up a lot of energy. They suck up a lot of energy, and it's very hard to change the temperature of water. Has anyone ever, okay, I shouldn't say has anyone ever done this. You know, you put like a taco or something in the microwave. How long does it take to heat up that taco? How long do you have to put it in the microwave?
Like
30 seconds. It takes 30 seconds to heat up a taco or whatever else. I don't know. How long, now if you want to make tea, how long do you have to put that mug of water in there?
2 minutes.
Yeah, like 3 minutes, 4 minutes, and then have you ever noticed too, like you put the mug in there, don't drink from that mug because it is like lava hot. It's so hot. Sometimes the mug is like really hot and the water in there, it's still cool. You know, it's like lukewarm and the mug is really hot. Why? Because the mug has a different heat capacity, right? The mug heated up really fast, but the water takes time to heat up. When I make tea, I usually like heat it up in the mug and I pour it in a different mug because the mug gets so hot, like burns my lips off. Does anybody else do that? Yeah, it's like that. And you got to put it in there for like 5 minutes for it to get, yeah. So anyway, why? Because of the heat capacity of water, and because water is a polar molecule and it makes hydrogen bonds. Those hydrogen bonds suck up all that energy. It takes a lot of energy. Okay. So this is the thing I want to get in your minds. It takes a lot of energy to heat up water. It takes a lot of energy to heat up water, and water holds a lot of energy. Okay. It's just great at holding energy. It's just really, I mean, look at it. It's way beyond anything else. It's like double the heat capacity of the second runner-up, right? Just about double. Okay, so oh yeah, this is what I was talking about. So farmers in the San Joaquin Valley in California, where they grow a lot of oranges, when there's a freeze coming through, you know what freezes do to citrus, right? They can destroy the plant. So what the farmers do is they will literally saturate. They'll leave the sprinklers on, and they will just saturate their crops with water. And the reason that they do that is as that water freezes, it releases heat. And actually, a lot of that heat gets transferred into the tissues of the plant and into the tissues of the orange, and it prevents it from damage. And actually, it stops the temperature from dropping inside the tissues of the plant. So that actually they can actually save their crops that way by absolutely saturating the oranges with water. Like they just leave the sprinklers on all night as it freezes. So I thought that was kind of interesting. You know, so it's using the latent heat. Because Because like I said, when water freezes, it actually releases heat. Okay. All right, so now I want you to think about this latent heat in terms of just global, what's going on globally with the oceans. Because guess what? Some parts of the oceans evaporate more than precipitate, and some places of the oceans precipitate more than they evaporate. So I want you to look at this map. That is a really important map. Again, this is something that comes up a lot in this class, okay? I want you to take a look at this map. Now, the colors that you see is evaporation minus precipitation. Evaporation minus precipitation. So if you're kind of that greenish color right there, that's 0. That means that you're perfectly balanced with evaporation and precipitation. So it evaporates as much water as it precipitates. Places that are red have a lot of evaporation and not as much precipitation. Places that are blue have more precipitation than they get evaporation. Okay? And you notice it's not constant everywhere, right? Some places have more evaporation, some places have more precipitation. Now I want you to start thinking about this in terms of energy transfer. Because evaporation is going to, right, just like think of the steam that evaporates off your body to cool you down. These places are going to they're getting cooled down. It's sucking up energy from these areas. And the places that have a lot of precipitation, that they're bluer, are receiving more energy. So really, you can think about the way that literally what's happening is we're moving energy from these latitudes where there's a lot of evaporation and moving it to these latitudes, kind of higher latitudes or along the equator where there's more precipitation. Does that make sense? So I want you to think about it. Okay, so take a look. Where do you see a lot of evaporation at? So right here, right? That little weird dot right there is Hawaii, by the way. You can see how there's like a little dot in the middle of the redness. Okay, so we can see it. It's actually at latitudes along the tropics. So those are actually the tropic lines. When we study circulation of the atmosphere, I'm going to explain why we see that. But for right now, I just want you to take it for granted that we see a lot more evaporation at the tropic lines. We see a lot of evaporation at the tropic lines, less precipitation. Where do we see a lot of precipitation? What's that?
Near the poles.
Near the poles, that's right. So higher latitude. Also, we see a lot along the equator, too. So we see a lot of precipitation along the equator and in the higher latitudes and mid-latitudes. So I want you to think about what's happening. This is actually a great thing. Is it hot at the tropics? How about there around Saudi Arabia in the desert? Pretty hot, right? Okay. So the evaporation is actually cooling things down. The evaporation is cooling things down. And that energy is being transferred to the mid-latitudes and the colder latitudes. Look at that, Canada, right? The coast of Canada, Siberia. Look at Europe. Okay, and it's being moved. That energy is literally being moved to colder places, and then condensation, precipitation happen, and there's a release of latent heat, and that actually warms the place up. So if we didn't have oceans, we would have much, much worse extremes of temperature. So the hot places would be hotter, and the cold places would be colder. Okay? So you can kind of almost think of, so this releases, when it's precipitating, it releases latent heat. When it's evaporating, it's sucking up latent heat. And so you can see how these are the evaporation latitudes, the tropic lines. These are the higher things like in Europe and Canada. That's more the precipitation latitudes. So it's depositing that energy. So you can actually think of the oceans as almost like a thermostat. They're regulating the temperatures. They're keeping the temperatures more steady on Earth. And thank God for it, because it's really like, boy, it would be much less like inhabitable planet if we didn't have this kind of thermoregulatory action of the oceans. Okay, I have not gotten as far as I wish, and I'm getting pretty close to the time, and I kind of don't want to open up a whole new bag of worms here. We start talking about density. So I think we're going to answer number 21. So you should be up to number 20, right?
Mm-hmm.
We're going to answer 21, and then I'm going to knock off, okay? And then we'll cover the other thing, density, next time. So just FYI, another thing I want you to be aware of, and this comes up a lot in this class too, the land heats up much more quickly than the oceans do. So why does the ocean heat up slowly? Well, one reason is that, again, we talked about this, the high specific heat, the high heat capacity of the water. So it's hard, takes a lot of energy to change the temperature of the water. Also, another thing, radiation from the sun, the solar energy, well, the water is partly transparent, right? So that radiation from the sun is heating up 300 meters of water instead of just the top, 1 inch of the land. So it's able to spread out that solar radiation over a kind of a thicker slice of the surface. Also, the oceans are able to mix. So that means that hotter material is able to circulate with colder material. So that also helps to keep the overall temperature down. And also, the evaporation of water lowers the temperature. It helps keep the temperature regulated. Because remember, evaporation is going to suck the energy up. It's going to keep the energy more regulated. Land, on the other hand, rocks and sand and dirt and all that stuff, it heats up quickly. Radiation doesn't penetrate the surface. It only heats up the top, inch of the land. There's no mixing of heated top material with the cold material. We're not mixing up the soils and rocks, right? They just stay put. They don't circulate. And of course, there's not as much water on the land as there is in the ocean, so there's not as much evaporation to remove that heat. Okay. So that's the answer, number 21. And I'm going to leave it there and let you go for the day, and then we'll talk about density. We'll take up density next time. And I'll see you all. Leave your lecture assignments. I'm going to have everything graded for you, by the way, for Wednesday. We'll leave it there. Okay? So you all have a good few days, and I'll see you Wednesday. And I'm going to stop this camera.